In pharmaceutical manufacturing, a drug's ability to heal or harm comes down to microscopic margins. The efficacy and safety of any pill depend entirely on the exact chemical dosages packed inside. Because the stakes are so high, global regulatory bodies like the FDA and the EMA mandate validated data demonstrating that every batch meets specific potency standards within a strict, documented range. To provide this proof, laboratories rely on a technique called high-performance liquid chromatography, or HPLC. This specialized instrument pumps a liquid sample through a pressurized column to separate complex chemical mixtures into their individual components. Patient safety and ultimately a drug's legal and medical viability hinges entirely on how accurately scientists interpret the data that this machine spits out. This chromatogram graphs separated chemical compounds as distinct peaks along a timeline. To calculate how much compound is present, our intuitive instinct is to measure a peak's height, tracing the vertical y-axis straight from the baseline to the tip. The basic assumption is that a taller peak corresponds to a higher concentration of the chemical in that sample. However, peak height is a byproduct of the physical conditions inside the chromatography column. Because these conditions are subject to minor fluctuations in temperature and flow rate, the height of a peak can shift even when the amount of chemical remains the same. If we rely on this single vertical measurement for quality control, we may base our dosage calculations on a metric that changes with the environment. To understand why this measurement is unstable, we have to look at the physical reality inside the column. As a tightly packed band of chemicals travels through the system, those minor fluctuations cause the molecules to spread out and widen longitudinally over time. This animation shows what happens on the graph when that band spreads out. The tall, narrow peak transforms into a short, wide peak. Its vertical height drops significantly, even though the total mass of the chemical remains exactly the same. Because peak heights are inversely related to their widths, height alone cannot provide a consistent measurement. A perfectly valid sample might fail a test simply because its peak flattened and fell below a specific height threshold. The superior geometric solution is to ignore the tip of the peak entirely and instead calculate the two-dimensional area under the curve. When you calculate the total square units of the curve, the mathematical rule becomes clear. Peak area remains constant regardless of how much the width fluctuates. The area is directly proportional to the true concentration of the chemical. Upgrading from one-dimensional height to two-dimensional area integration provides scientists with an error-proof parameter. It isolates the mass of the compound while ignoring the physical chaos happening inside the column. Once we have the geometric area, a mechanical question remains. How do we translate abstract square footage into a specific real-world chemical weight, like milligrams? We do this through a process called calibration. Analysts inject standard solutions into the HPLC system, samples that have known exact concentrations of the target chemical. This chart displays a calibration curve. Scientists calculate the peak areas for those known standards and plot them on this grid against the exact amount injected to establish a baseline. Looking closely at the linear fit of these points, we find the response factor. This value is the mathematical slope of the line created by plotting our known reference points. With this slope established, the final equation is straightforward. For any unknown sample, we take its measured peak area and divide it by this response factor to reveal the exact concentration of the drug. The calibration curve provides the specific ratio needed to convert abstract geometric shapes from the chromatogram into definitive, actionable dosages. Even with perfect area calculations, we still have to account for human or mechanical error on the front end. The actual physical act of injecting the sample via syringe can introduce tiny uncertainties in the starting volume. To bypass these injection errors, chemists employ a technique known as the internal standard method. A carefully measured quantity of a completely separate known substance, the internal standard, is added into every single sample before it enters the machine. As seen in this diagram, scientists evaluate the ratio between the two compounds. They compare the target drug's peak area against the internal standards area. If a faulty syringe reduces the total sample volume injected, both peaks shrink proportionally on the graph. Their relative ratio remains exactly the same. Using area ratios effectively cancels out any physical injection irregularities, providing a foolproof safety net for the analytical data. Raw HPLC analysis is highly susceptible to the real world's physical chaos, from shifting flow rates to microscopic injection volume errors. By utilizing two-dimensional area integration and internal standards, scientists systematically strip those physical errors out of the equation. This rigorous geometric translation process is precisely what satisfies good manufacturing practices and keeps pharmaceutical companies in compliance with strict international regulations. The exact area of that trace on the lab monitor serves as the definitive proof, the final guarantee of a medicine's safety, purity, and exact dosage.